Well, as promised, this next section, and it's actually the last piece of what we're going to talk about before we start preparing for the CLEP exam, are exponential and growth and decay questions. This has to deal with population growth or bacteria or half-lives. Obviously, those of you in chemistry have probably dealt quite a bit with this. And so the original exponential growth and decay you actually saw back in pre-calculus. It's just that they would give you all the information you would need and treat it like it's an e to the x question. And so you'll notice that in our homework packets, we've been preparing for this by doing some e to the x questions and just familiarizing yourself with ln and with e again, because it's important that you can do those pieces before we start, obviously, asking you to manipulate an equation or to do the derivative of it. Now, this version that we are looking at here on the left-hand side, A represents your final population. Okay? And this is called A naught. This is not A sub 0, although some people might say that. Frequently in the math world, we don't say that. We will say A naught, and that means initial population. K is what we call the growth, and of course decay or decay constant, depending on what we're talking about. It is a constant. Sometimes we still have to find it, same with the initial population. Those are constants. They are not a variable of any kind. Whereas T is going to be a variable, and of course that represents time and always will. So this is exponential growth and decay. And once again, you see how E has shown up its face again. It's not just limited to what we have done in the past with LNs. So as we talked about when we first introduced E, the E shows up in more than just one area. And so in particular, this is where we see E especially. So we have final population, the initial population, those are represented by the A's there. We have our growth and decay constant, and then we have time. Now this formula you see here on the right is actually the same as the one on the left. And you're like, how can that be? Well, the first thing I want you to recognize is that it is, in fact, writing it as the derivative in respect to time. So just to prove it to you, I'm going to take the derivative, okay, with respect to time of our equation, A equals A naught e to the kt. Oops, I should have bracketed. Okay, so what does that look like? That means the derivative, to start, would be the derivative of A with respect to t equals, now when I do the derivative of the right-hand side, I want you to keep in mind that A naught is a constant and K is a constant. So A naught isn't really, it's not like we have to do the product rule here. We're really just doing the derivative of e to the kt. So I'm just going to leave that A naught outside, just like I'd leave a 2 or a 5 or any other number outside, and do the derivative of e to the kt, where that variable is in there, t. And so the derivative of any e to the x is e to the x, or e to the kt in this case, times the derivative of whatever's in that exponent. And of course that would mean k. Now just to do some little mathematical finesse here, calisthenics, we're going to move k outside instead. And just kind of flip-flop, because it's multiplication. We know by the commutative property of multiplication that we can actually flip those around. It still means the same thing. Doesn't matter which order in which you multiply, right? And so then what I want you to recognize is A naught e to the kt is the same as that equation, or whichever one you want to refer to, that we started with. A equals A naught. That's what this is, right? And so we can replace this with A. And there you see, we have in fact proven the fact that what you have here. Sometimes, and I'm going to show you an example here in just a minute, they will write the exponential growth and decay question as you see here on the right. And you need to recognize not only does it mean exponential growth and decay, that it involves E, and what these things all represent. What they'll give you is usually a K, or a growth constant in that information. So they're giving you that piece. And so maybe you don't know the initial population or the final population, but they're giving you K. Many times the word problems won't give you K, so we have to be able to address both. Let's look at an example. If dy dt equals 4y. Now I want you to first of all see that this is in fact an exponential growth and decay, even though it says dy. And you're like, but it doesn't say dA. I know. I want you to be familiar with the fact that it can change the letters. It doesn't have to strictly say A to point out that it's exponential growth. Now you might think, well, how do I know then what that is? Well, It's just by practice, I guess, and by recognition of it. But here's a CLEP question, actually. And you might even find this in your homework assignment. I believe it is, in fact, number 11. So it says if dy dt equals 4y and y equals 3 when time is 0. Do you see how this information is kind of telling you, okay, we've got initial going on here. When time is 0, the initial population is 3. Find the value of y when, and then it gives you different values for t. So what this is telling me then is that 4 is k. And so in looking at a equals a naught e to the kt, we actually have quite a bit of information. I know a naught. A naught means when time is 0. And so that means that we have 3 e and we have 4 in place of k. This is actually quite a bit of information. Now when they say, all right, for part A, what happens when time is 1? What you're going to do then is you're going to plug in 1 for t. And so we would have e to the 4th there. So 3 times e to the 4th. Easy, right? And then for B would just mean that you have A equals 3e to the 4 ln 2. And we have to remember what piece in doing this with e and ln's. My hope is you recall that that 4 has to move, and then the e and the ln can cancel. And so we would, in fact, actually have 2 to the 4th times 3. And I'm going to leave it to you to finish that because that is part of your homework. The half-life question. Here we go. The half-life of a radioactive substance is 2,000 years. If the initial amount of the substance is 4 pounds, how much of it will be left after 1,000 years? I want you to think about all the information they're giving me here first. The first thing I want you to say, or see here, is that A naught is 4. I also know that after 2,000 years, that means when time is 2,000, that I have half of the amount. How do I know that? Because it says half-life, right? That means that half of its value happens at 2,000. So that means that half of 4 is 2, and so that must mean what happens after 2,000. And we're going to use this to find k. And then once I have that information, once I have that constant k, then I can determine what happens when time equals 1,000. Okay, so there's a couple steps to this. In the past, in pre-calculus, when they would have told you what the growth constant is and then just told you, asked you to find the time at 1,000. That's what they would do. Okay, so how do I use this? Well, I've got 2 equals 4. That was my initial. E. K we don't know, but time is now 2,000. And so from here, we're going to divide. 2 divided by 4 equals e to the 2,000k. And then how do I get rid of e? Good. Ln both sides. So hopefully you're okay if I leave this as ln, and I'm going to ln both sides. And I have 2,000k here. Now before I go too much farther, I want to make sure that we know how to rewrite this. And at this point, my hope is that you understand that that's negative ln 2. If you do not, please come see me about ln's. But the bottom line is that could be written as 2 to the negative 1, and the negative 1 would run in front. Or you could see it as ln of 1 minus the ln of 2, and ln of 1 is 0. Either way, you get negative ln 2 divided by 2,000, right? You're like, oh, that's ugly. I agree. So what we have then for our k is negative natural log of 2 divided by 2,000. So what we're looking at then is that a equals 4e, and in the exponent, negative ln 2 over 2,000 times the time. And so if I want to know when time is 1,000, then that means that what I've got here is I'm going to put in place of t, I'm going to put 1,000. And so just to make my life a little bit better, I'm going to divide that out automatically and recognize that that just puts a 2 down here at the bottom. So I have a equals 4e negative natural log of 2 over 2. And so you're like, well, can't we neaten that up at all? Well, we actually can. Because in multiple choice, you probably wouldn't see that as an answer. Let me do it this way. I'll rewrite it as this, negative 1/2 ln 2. Can you follow that? So that 2 I just brought to the front of that. And then recognize that we got to get that out of the way, so that becomes 2 to the negative 1/2, right? And the e and the ln would cancel out, so I have 4 times 2 to the negative 1/2, which is 4 times 1 over the square root of 2. And so then I could keep going. We can rationalize the denominator if I still don't see the answer. And so I would have these would give me 4 square root 2 over 2, and the 2's would divide out, giving me 2 root 2. And that would be the final answer. Wow, isn't it amazing that this ugly looking thing can reduce to negative 2 root, or not negative, sorry, to 2 root 2. Impressive. All right, let's see if we can do another example. If the world population is growing exponentially, doubles every 20 years, how long will it take to triple? So once again, it doesn't look like we have a lot of information, but we actually have plenty. Just to go back to what we're dealing with here, we certainly weren't given K, but we do have some information. What we do know is that we have the world population and it's growing exponentially, so we understand that's using the growth context, and it's doubling every 20 years. So whatever you deem as being A naught, and at this point you can choose whatever number you want, and you can say it as X, you can leave it at, whatever. Let's say it starts at 5. Let's say whatever you want it to be. I mean, if I said 5, then that means after 20 years, it's going to double, right? So after 20 years, it's now at 10. You could have said 2 and 4. You could have said 3 and 6. You could have said X and 2X. It doesn't really matter what you choose for A naught, but whatever it is that after 20 years, it's going to double. And I'll show you why it doesn't matter. So now what we're going to do is we're going to plug this in. So I have 10 equals 5. E, again, we don't know what K is, but we do know that in 20 years it was supposed to do just that double, right? So if it was X, 2X, right? Whatever. So what's the first step I'm going to do to solve for K? I'm going to divide by 5. And when you divide, or divide by X, or divide by 3, when you divide by that, let's just say it was X, you follow that when I divide this side by X and this side by X, I'm left with 2. And no matter what you would have chosen here, whether it was 6 and 3 or 4 and 2, you would have ended up with 2 here equals e to the 20k. And so we can solve this because we know we can get rid of ln. That would be the ln of 2 equals 20k. And I would divide by 20. And so that's my growth constant. It asked me, what is it going to take for it to triple? Right? Once I recognize what this is supposed to be, I want to know what time is it going to be triple. I want to know when it's going to be 15, right? And so, or, 9, or whatever you're dealing with, right? 6 if you're dealing with a 2, or, whatever your initial started at is, or x to become 3x. That's where you want to pick up with. So what we want to do is you're then going to just set this up, and I actually would like you to do it from here. I want you to set it up with, hey, I want it to be 15 now, 5e, now using your growth constant. That's what you would do. So go ahead and finish that, and for class tomorrow, that's where I'd like you to end, and that's exponential growth and decay.